Okay, thank you for coming to this session. This session will cover the overview of the SPDK and the Ceph and their latest status on AArch64 platform. And later we'll introduce how to use SPDK to accelerate Ceph workloads on AArch64 platforms. So for SPDK, what is SPDK? It means Storage Performance Development Kit. It's a set of tools and libraries to create high-performance user mode storage applications. So from the architecture diagram, we can see that SPDK stack is split into three parts. There are drivers, storage services, storage protocols. The NVMe device drivers in SPDK it works in user mode. So it uses several techniques to minimize the software workloads, software overhead. It works in user space, so it avoids the interrupt latency. And also, it avoids the user kernel context switch cost, which further reducing the processing latency. And it uses lockless design, which avoids the data synchronization overhead between threads. Above the drivers, there are storage services. SPDK defines called block device abstraction layer, which export and operate different block storage devices. And at the top of stack, that's a storage protocol supported by SPDK. So as this stack is designed for new storage hardware devices, SPDK can achieve millions IOPs per core with better tail latency. For the latest status of SPDK on AArch64, we have several ARM-related patches have been merged by upstream. Most of these patches have many focus on two scopes. The first one is memory barrier. The memory barrier patch implements essential read and write barrier operations on AArch64 platform. And another patch is about virtual address space. Because SPDK is originally development on x86, so it has an assumption that the virtual address is always 47 bits. But this is not true for AArch64 platforms. On AArch64 platforms, we support two kinds of VA address settings, 42 bits and 48 bits. So without the VA patch, 42 bits works fine, but 48 bits will fail. So later, upstream has bumped the VA max VA address space to 48 bits. And we have verified SPDK 1710 release on AArch64 platforms. The verification is done with 4.11 kernel, 4K page size settings, and we test both 48-bit and 42-bit virtual address space, and both UIO and FIO modes are tested. So regarding the performance test, we measured the performance in two ways. The first one is called SPDK Perf. It's a tiny tool, including SPDK source code. This tool is mainly used to benchmark the NVMe device drivers provided by SPDK stack. So you can see from this screen, I'm not sure if you can see it very clear, we can achieve IOPs for nearly 300,000 IOPs, and for bandwidth, well, nearly is almost 1.1 gigabytes per second. So these benchmark results have reached the upper limit parameters listed on the NVMe SSD card. Another popular tool called FIO was also tested for SPDK on AArch64. We run three test modes called random read, random write, and random RW, which is mixed operation of read and write. So you can see from the chart, the blue one is kernel driver result, and the orange one is SPDK driver result. We can see that from the chart we can see that SPDK can achieve almost 27 times in IOPS and bandwidth comparing to kernel NVMe drivers. And the FIO configuration is listed as here. We use the IO depth is set to 32. And this is a latency result for SPDK FIO test. This is the 50% latency, and this is 19% latency. So from the chart, you can see that SPDK has better performance in random read and in write operations in random write, but it has worse performance in random write and in read operations of random RW. So it is very interesting that we found that it has extremely latency delay, tail delay in 90%, and in the read mode of random read and write. So we are still working on this to identify the root cause. So for next, of course, we will continue our investigation on the latency issue. And as SPDK uses CRC to do the checksum to verify the data integrity. So, and ARM has crypto extensions to accelerate this kind of routines. So optimization can be done with ARM's ASMD instructions and crypto extensions. Also, as AArch64 support two different kind of kernel page size settings. So providing with these different kernel page size settings can give us hints or some clues to find how to improve the SPDK performance for on AArch64 platforms. So about to the Ceph. Ceph is a unified distributed storage system designed for performance, reliability, and scalability. Ceph has two kinds of backends, which called file store and block store. File store is a legacy one, which store the objects in Ceph storage, and block store is a new one, which designed for better performance. On above the backend, this is Rados, called Rados. Rados is the core service to managing Ceph storage. And for high-level applications, like they can access Ceph storage either by Rados, calling label Rados directly, or they can access different storage services exported by Ceph. Say Rados Gateway, this is for object storage, and Ceph RBD, this is for block services, and this is Ceph FS, which export POSIX compliant file interface. And this diagram illustrates how Blue Store works. Blue Store consumes the raw devices or partitions. It stores data via asynchronous libel infrastructure, and it stores corresponding metadata to RocksDB. RocksDB is a key-value database which designed for high-speed storage devices. And BlueStore, it provides full data built-in compression, and it provides full data checksum. You can use CRC or other hash to do the checksum. For the latest status of Ceph on AArch64, we have validated and released Ceph packages in Linaro's ERP release by Linaro SDI team. And we have integrated the Ceph with OpenStack. In OpenStack, Ceph can be used as a backend storage, which works for Cinder, Glance, Nova, or Swift. And we have commit patch to community to improve the Ceph's functionality and performance on AArch64. And Ceph performance tuning is still ongoing. Okay, so to enable SPDK in Ceph, this we can check these diagrams. This is a file store, and this is BlueStore with SPDK support. So for now, SPDK works only with BlueStore. It cannot work with file store backend. So compare these two backends, we can find that to enable SPDK in Ceph, we have to first you have to replace kernel NVMe driver with SPDK's user mode driver, and as SPDK's NVMe driver works in user mode, so Ceph developed another abstract block device module called block device on top of SPDK's driver. So other components in Ceph can access SPDKs through this block device module. So to deploy Ceph on top of SPDK on AArch64, it can be very straightforward. So we list the brief steps here. So for your so you can check out. So first, you need to configure your kernel with the huge page enabled, and you need to set the huge page parameters. The default setting is 1024 2 megabytes huge pages. So first you need to enable huge page features. And the second step is to build Ceph. As we have submitted quite a few patches to the upstream and to enable SPDK function on AArch64. So and this patch has been merged by upstream. So you just pull the source from head at master branch. That would be okay. And in the source code, SPDK is set to on by default when you build for AArch64 platforms. The third step is to get NVMe device serial numbers. You can use this command. This is just an example for your reference. To get all NVMe devices in PCI information to extract these informations. Then you need to use the serial numbers displayed in this information to create a Ceph configuration files. Then deploy Ceph as usual. The last step is to check Ceph status with a command ceph-s to check if your SPDK is really working and if your Ceph status have any problem. So the last step is to check your status. Of course, and we have very detailed steps and how to deploy Ceph. So you can check this wiki page. It's on Linaro wiki.linaro.org. This give detailed information and steps and the commands. They are all listed here. So, FL was also used to run performance tests. This diagram shows how we set up the test environment. We create a Ceph cluster with 2 nodes, and each node have 1 OSD, and have 1 monitor, no MDS, and a Redos gateway. For each OSD, it has 1 PCIe. It has 1 NVMe device attached, and the platform is using a 2.4 GHz multi-core CPU. And for the client, it is a 2 GHz multi-core CPU, and we benchmark the performance with the case that with sequential write with different block size, ranged from 4 kilobytes to 16 kilobytes. And we also test with different FIO stream numbers for 1 and 2. And this is a chart to describe for the test results. We can see that for IOPS range from 4 KB bar kilobytes to 16 kilobytes. Ceph data is this one, and this is kernel NVMe data. So we can see that in IOPS we have modest improvement compared to NVMe drivers. It's about 5% improvement. And for latency, we can see that it has a latency drop, and it's about 10% drop compared to kernel NVMe drivers. Also, we can see that it has good nonlinear scaling compared when you increase the CPU cores. This is 1 core, this is 2 core, and this 4 cores. So it has good nonlinear scaling when you increase your CPU cores. And this chart gives the results for 2 FIO streams. We can see that also it has improvements in IOPS, while the improvement is not as significant, but it has. So from result, we can see that with SPDK integrated, Ceph can achieve more IOPS and with lower latency. And it also remains good nonlinear scaling while the number of cores increased. So, from the previous result, we can observe better performance improvement. But as I mentioned, the improvement is modest, not that significant. So, our major work is to continue to tuning and improving Ceph performance on top of SPDK. And there are several ways to do that. One is to enable zero copy in Ceph. Using zero copy, we can avoid extra memory operations and remove the lock during buffer allocation and release. And second idea is to simplify the locking in Ceph to improve the OSD daemon performance. And as mentioned before, in SPDK, ARM architecture support different kernel page sizes, so we can switch page sizes and test them for 16 kilobytes and 64 kilobytes to improve the memory performance. And when you change the page size settings, so you may also need to change the NVMe device code. This code is in Ceph to improve its performance associated with the different page size settings. That will be all for our latest status and benchmark results. So, okay. Thank you for listening. So, any questions? Yes, please.
Have you done performance comparisons with x86 using basically the same test setup?
We have actually we have done similar settings on x86 platforms. We have done some other kind of test before, but I mean what I mean is we didn't test use NVMe card on x86. We just test for ARM itself. Okay.
问一下，是这么回事。就是那一个 SPDK 只是用在 NVMe 盘上是吧？普通硬盘也可以支撑。就是因为我们现在那个测那个配置，那就是硬盘和 NVMe 混合，就是再加一部分就那个做日志缓存嘛，然后存储还是用的是磁盘。
我这个那
English, please. Translate the question to English.
So, a question is about is a SPDK only target for NVMe device? Can it be used for hybrid hard drives like legacy hard drive with NVMe device to use them together? So, for SPDK, the design is for high throughput with low latency devices. So that's why it uses user mode driver to avoid the interrupt latency and context switch. So if you are using a traditional legacy mechanical hard drive, if you are trying to use such device with SPDK, so the design principle for SPDK, so they will not they don't exist because the spin latency for mechanical drive that will make SPDK's advantage make them don't exist. So it will not be good choice to use traditional hard drive with SPDK.
So that's the second thing. I mean, did you run it in target mode where SPDK was exporting the NVMe OF, or was it all just local, like the NVMe device was in the machine and then you were running?
Okay. So for the test cluster, we use SPDK to export the device as Ceph RBD devices. So we didn't use it as NVMe or Fabric.
Sorry, I have a question. Is SPDK can replace the file system? Does it need any file system?
You still need some kind of file system to work with SPDK, because SPDK just gives you acceleration to access NVMe storage devices. But you still need some, I mean, of course, you may not need some legacy file system like POSIX applied file system, but you still need some like object storage things like that, stuff like that. Yeah. So we can check this.
Just replace the NVMe bundle stack. Yes.
Yeah. And then can go back to this architecture. So SPDK just provide your acceleration to access NVMe devices, and it also can to export these devices through different abstraction layers. Like you can use it as a Ceph RBD to integrate it with Ceph, or you can use SPDK integrate called some file set called Blue Store or Blob Store, and over that you have Blob FS. So You can add any file system or storage access way to SPDK. Yes.
Would you mind share what kind of the ARM hardware you're testing with?
For ARM hardware, I can only say we are testing with ARM V8 platforms with multi-core CPU, but I cannot give you the detailed information of the vendor. Okay, so no more questions? Okay, thank you very much. Thank you.